Welcome to Astronomy Lesson 5.1, Intro to Stars. And who doesn't like Chris Pratt? Okay, there we go. So what is a star? A star is going to be a luminous sphere of plasma. So luminous means it gives off light. And it is held together by a balance of its own gravity, which is sucking it in, and nuclear fusion, which is pushing it out. So, kind of a quick baseline there. Most of the stars in our universe that we have that are known to us are composed of hydrogen and helium, which are left over and resulted from the Big Bang, not the theory, not the show. And the color of a star is based on the surface temperature of that star. Now, this is kind of backwards than what you might be thinking. I'm going to move this out of the way over here. Where red is actually cool and blue is actually hot. So kind of opposite that you might think. Alright, so spectrum of stars here. So these are all the spectral classes of stars. Stars are separated into different spectral classes based on their spectrum. And I will zoom in on this so that you can see it better. Zoom. No, zoom it. Okay, there you go, zooming. Alright, so here we have spectral class O. This is our dark blue. These are our hottest stars, probably young as well. Blue stars, which is spectral class B, and spectral class A, which is a light blue, followed by spectral class F, which is our white stars. And then we have spectral class G, spectral class K, and our cool stars, which is spectral class M. How fun! Alright, so what's happening inside of our star, and we zoom back out a little bit here, is we have nuclear fusion. So what we do is we take some hydrogen, move them really fast and close together, generating lots and lots of friction. That friction generates heat, and once the star's core temperature gets hot enough, around 10 million degrees Kelvin, then what's going to happen is they're going to start to fuse together. And what we're going to get out is helium. Now that's for most of our main sequence stars, or most of the stars that we have. Older stars, they're going to do something a little bit different. They're going to end up running out of that hydrogen and just have helium. And that helium is going to need to fuse together and fuel that star so it can continue giving off its luminous light. And it's going to form heavier elements. Once a star's life cycle gets into this phase, it's going to start to run down pretty quick. So we're using larger molecules, a lot more energy. We're going to start running out real quick. Alright, so periodic table breakdown. So this periodic table, which is a list of all the elements separated by atomic number, which is the number of protons. Chemistry people. Can't see me, but I'm making faces with my face, because what else would you do with your face? Anyways, and this shows where they've come from. So purple are from our Big Bang. These are large stars making our heavier elements. Blue stars, these are going to be when ions are reacting with cosmic rays. We have some of them making some of our smaller stars over here. Supernovas are creating these. And then, hey, why not? We made these. That's us. Go humans. We are awesome at making things and having them not last very long. Alright, so stars around us. The closest star to us is our sun. And it's approximately 149 million kilometers away. So pretty far, and that's an average because of our elliptical shape of our orbit. Because light speed is not infinite, which means it doesn't happen instantly, it actually takes time to travel, there is a speed limit to which light can go, and it cannot go past this. And interesting enough, it's also the fastest thing that we know of in the universe. So the speed of light is 300,000 kilometers per second. That means that for every second it's able to travel 300,000 kilometers. So yes, this is very, very fast. Light is very, very fast. That's why it's the speed of light, fastest thing we know of. The sun, which is 149 million kilometers away, gives off light. It's a star. It's luminous. It's radiating energy. That light has to travel all the way through our solar system, our inner part of our solar system, through space, go around, you know, a couple planets, some moons, and reach here on Earth. So how long does it take? So what we're going to do is we're going to take the distance that the sun is, so 149 million kilometers away, the speed, 300,000 kilometers. We're just going to take that distance, divide it by the speed, and we'll get the time. And the time in seconds, apparently I didn't write the time in here. Oh wait, it's on the next slide. Haha! The time in seconds is around 500, and then 8.3 minutes for light to reach Earth. That means whenever you look at the sun, you're actually looking at it in the past, approximately 8 minutes ago, which is kind of crazy to think about it. So what else is by us besides our sun? So those of you into Star Trek, you might have heard of Alpha Centauri or Wolf 359. These stars are close-ish to us, right? So here's our sun. This is the outer edge of our solar system in the Oort cloud. That's where we believe comets have come from, at least the long-range ones anyway. Then we have 2 light years. 4 light years away, we get our Proxima Centauri, Alpha Centauri, and Beta Centauri star system way over here. So the light from those stars take 4 years to reach us. And here's a quick breakdown of stars based on their distance to us. So Wolf 359, 7 light years, Ross 248, 10 light years. So it takes 10 years for that light to reach us. Alright, I'm going to go ahead and pause the movie here, and I will re-up with 5.2 star classifications later. Okay, hasta luego, peoples. Goodbye.